please.
Yeah.
I don't know who gave you the idea, or if you had the idea, but I love it. Excellent. It's very, very clear. All right, Jayanta, do you want to share the screen, or do you want to share it, you think?
Yeah, I can share it.
Cool. So so today we need to decide two things, you guys. Number one, whether our data is good or not. And number two, if we want to continue or stop and write up the paper. So let's go to point one first, right? Oh, sorry, you think I need to allow you to share multiple screens. Oh yeah, done.
Yeah, okay.
Cool.
This one. I see the PowerPoint.
Yeah. Yeah.
Okay.
All right,
so
cool.
here's okay.
Maybe you want to go into full screen mode.
Full screen mode. Okay. Can you see the full screen?
We can. Thank you.
Yeah. Okay. Great.
All right.
So here, let's recap the progress that we made for the last month. And here's a table I made because I think there is still some data missing in the folder, especially for the cadmium and the antimony doping. And there is 2 CTA data missing. And for SPS sample, for these 3, especially the pristine and the bismuth doping, the FA is still passed to Emory, I think, right?
Okay.
Yeah, so we don't have the thermal transport data yet.
But it will come probably next week, so that's good.
I hope so.
Okay, yeah, me too.
So here we only have the first sample that we made without joule heating, so it's not the properly joule heating one.
Okay.
So I doubt whether it's correct or not, so maybe wait for the 3 to get the data.
Okay.
And for cadmium doping, I finished the joule heating and still wait for the SPS sample.
Okay.
And
when will that happen, Jayanta? Okay. Well, that's 2 samples, right? Perfect. Please, you think make sure the powder is like well sealed and well stored and there are no contaminations.
Yeah. Okay.
Singapore is very wet, very humid, right?
That's right.
Sorry? Yeah, you can put them in the vacuum oven, just to make sure that nothing happens.
Yeah.
That's what I would do.
Right.
But yeah, okay, fine. Okay, let me think for a minute. 5%. Okay, let's go to the data.
Data, okay. So here's the EDX.
Right.
Yeah. And I think the 5% bismuth, there is some precipitate and it's not evenly separated for this one.
Yeah.
And I think in previous joule heating one is, let me think, how can I switch to, yeah, this is the previous joule heating data.
Yeah.
And in this one is there is still precipitates here. So
yeah, I can see them.
I don't know the reason.
Yeah, probably because 5% is no longer soluble. Okay.
Okay.
But the 2.5 is fully dissolved.
Fully dissolved. I think there is some precipitates here. I just not put in the graph. There is 3 sets of here. This one. This one. There are still some precipitates here.
Right. We should combine both presentations.
Okay. So I put the joule heating EDX in the presentation, right? The previous one, this presentation. You see, so this one is good.
Yeah, that's fine.
Yeah, this one.
That's a 2.5?
Yeah, 2.5. There's still precipitates here.
That's fine. Okay, so please combine everything in the same slide and label things nicely. So whatever is just joule heating, just write joule heating. Whatever is joule heating plus SPS, write joule heating plus SPS.
Okay.
So at the end of the day, we're going to write a paper with all this data. It makes sense to have it in the same place.
Okay, okay.
Then when we have to
combine two of them.
Yeah, precisely. So when we have to put the figures together, like they are all in one place, right?
Yeah.
Of course. Yeah, I mean,
okay.
it depends on like, yeah, we can unify that, right? That's fine. We can unify that. So
Okay.
so normally what I do is I normally take 3 pictures at different scales,
Three
and
pictures.
large, medium, and
Uh-huh.
small, and then
Okay.
like, yeah, that's what I normally do.
And I'll put it in the slide, right?
Okay, perfect.
Okay.
All right, cool.
And here is the
Yes.
XRD.
Okay.
So on the left is the.
Can you go to full screen mode?
Full screen. Okay.
Thank you.
So for these two, the geranium emitter and the 2.5 base mode, this one with solid line is the joule heating one without the SPS. And the dotted line is the is we use
patterns are
SPS
pretty much
after
the
the joule
same.
heating. Yeah.
Yeah, there is a little bit of texture, but that's fine.
Yeah, and on the right is I have compiled all of the available data of XID here.
Yeah. Yeah, see, like 5% is already phase segregated.
Yeah.
When you add cadmium telluride, what happens? You have further doping. Okay.
Okay.
Yeah, we should get the lattice parameters out of this.
Lattice parameter.
Yeah.
Okay.
You guys, I know Gianta does. You think it'd be useful for you? Kedar told me that you, when are you starting your PhD again?
I think it's next year.
Next year, okay.
Yeah.
Right. I think it would be useful for you to learn how to use some sort of refinement software.
Okay.
Gianta's the one that knows how to use the most. He knows how to use Llana and Topaz.
Ask him.
I can also send you some tutorials that I personally like.
Great.
How I learned, to be honest.
Yeah.
You know, and it would be useful for you. In the meantime, Gianta, get this data and refine it and get lattice parameters so we can have a plot of lattice parameters versus doping to see where our maximum solubility goes and how much actually are we incorporating into the lattice.
Yeah, okay.
That'd be nice. That's easy anyway, but like, and it's not important. It's just like, we're gonna need it anyway, so we might as well get it early. Okay. Very good. Okay, so we have a lot of data, but that data is not telling a full story, right? I can see how we achieve solubility in the bismuth. We need more cat telluride data. Do we have 5% cat telluride?
Yeah, I think we have a raw data in the folder, but it's not transferred to the XY, so I can't plot it here.
No problem, no problem. That's fine.
I can do it next week.
Yeah, that's fine. Yeah, but just like, so we can have everything in the same place.
Yeah, okay.
Because looking at it like this is very confusing. So we should split it, right? Like, we should start with the base compound and then like, we start adding things, right?
Yeah.
Okay.
So for different doping elements, I can separate for different graph.
Yes. So you know, like the way we should do it is like, we start with bismuth, then we add cadmium, and then we add antimony. So we should start seeing where things like phase segregate, because that's when you stop, because all the dopants are not being substituted into lattice sites. They go to either interstitial sites or they crash out and phase segregate, right? Yeah. None of them are intrinsically bad or good. They are just what happens. So we need to know at what point does that happen. And having those different graphs with those lattice parameters will help us. Yeah. Okay, I can do that. So, I mean, it's not, again, it's not urgent. It's not a lot of work. You don't have to measure anything. You just have to replot. And then Gianta needs to do the analysis, but that's really fast because we already have a functioning Topaz model that I built before I left. So you just need to take the model that I built and just like substitute data and refine it. And then take the lattice parameter, right? Like, you don't need to build a model yourself from scratch. I already did that for you guys. Yeah, okay. All right, what else?
And for next one is
wonderful.
the
Okay, so JH means joule heating, right? So this is no SPS.
Yeah, no SPS.
It'd be useful to have a comparison between the samples that we have SPS and the ones that we haven't in the same graph, so we can see whether the SPS. I don't expect. Oh, wonderful, good.
Yeah,
so can we look at this first then? Let's look at this first then. Let me see.
This first.
Yeah.
This one. Yeah. Okay.
Yeah. All right, so
I think the dotted line is the
Seebeck coefficient. Good.
Yeah.
The Seebeck coefficient changes quite a bit.
Yeah, I think the Seebeck coefficient, especially in the low temperature, it's really.
Yeah, I can see that. I can see
that. So I
that.
also conducted the measurement of the only joule heating one. It's used. We used the same palette for the SPS, but
very good.
Don't conduct SPS, and I measured the sample. So it's indicated in this square, the white square here. So I want to see if it's a synthesis problem or the SPS problem.
SPS probably introduces, don't call it a problem, it's not a problem, right? Probably the SPS introduces extra precipitates.
Yeah.
So that changes the Seebeck coefficient. In terms of power factor, however, we're pretty good. Man, 40, that's a lot. That's because the electrical conductivity is really high. Yeah. We still need to de-dope it a bit more. So, okay, so let's go to the the previous slides.
This one is only
that's fine.
SPS, and this one is joule heating.
Okay. So same here. Like we have a lot of data here, and that's really hard to analyze. So we should split it: baseline, single dopant, double dopant, ternary dopant, right? Like so. Well, okay, cool. So what I can see is that we are, as we introduce the dopants, we are de-doping the sample, which is exactly what we should be doing, which is good. So the scattering physics are normal. That orange sample looks really good, actually. That must have pretty low thermal conductivity. That must be good. The other promising sample, I would say, is the brown one. The one that has 5% cat telluride.
Yeah.
Because you see like 5% cat telluride and 5% antimony apparently. So that looks pretty good too. This data looks good, man. Yeah. Let's go to the thermal conductivity.
So thermal, let's see.
You are moving backwards instead of forwards. That's fine.
This one is the thermal.
Wonderful. Okay, so K total. Wonderful.
Yeah, we only got for SPS, we only got one pristine. Right. And this one is not joule heating correctly. So I
why does the thermal conductivity goes below zero into the -1? What's happening there?
Yeah, I don't know why.
How did you calculate that? Start there.
I think is the total minus the electric.
What Lorentz number did you use?
Lorentz number. Let me check my original file.
Okay. Jayanta, next week you're joining the let me check my calendar. The 7 p.m. My 7 p.m. The title of the meeting is called Rapid Synthesis. Are you joining? Package this nicely because you're gonna be presenting this. Yeah. By the way, Kedar is under the impression that the copper tin telluride compound is a new compound. But it's not, right? It has been made before. Okay, but that doesn't, Jayanta, I'm gonna give you the best piece of advice that anybody has ever given me, which is when people ask you a question, you answer the question they ask you. I asked you if it's a new compound, and you reply that the properties have not been measured. Thank you. See, this is good advice for your thesis committee, by the way. They will not be as nice as I am. Please believe me. Okay? So get used to answer the questions that you are asked, not any other questions. It will make your life incredibly easy in the short, middle, and long run. Not only with your thesis committee, also in conferences, and also when you apply for jobs. It changed my life. For the best, by the way. So I'd rather tell you now rather than later. You think this goes for you as well?
Yeah, okay.
Okay. Make your life easy. You want the person asking you questions to like you, not to dislike you.
Yeah, okay.
So you think, what are you doing next Tuesday at 7 p.m. California time? What time is the meeting, Jayanta?
7 p.m.
What are you doing at 10 a.m. next Tuesday, you think?
Next Tuesday, I think I have time that.
I'm gonna see I'm gonna see if we have time for you to present these as well, because you seem to know what's going on. Yeah, you're a bit more junior than Jayanta is, so Jayanta normally would do this because he has more experience. But it's okay. I want people to give us feedback on this as soon as possible. So I don't want to wait 2 weeks. Okay.
Okay.
Worst case scenario, I'll present this. But since you guys did it, it should be you who presents it. You know, like, I don't want to steal your thunder. This is good work, and I want you guys to get credit from everybody else.
Yeah. Okay.
So, all right. So where were we? What Lawrence number did you use? You think?
This one. This is the formula.
Right.
Yeah. This one. The M is the Seebeck coefficient.
Right.
Yeah. Used from that paper that we put in the group chat.
I know.
Yeah.
Okay, let's go back to the data.
Okay.
I'm sorry. Yeah, I'm gonna say something that's not gonna come as a surprise, you guys, but that thermal conductivity is wrong. We all agree, right? We all are on the same page there, correct? Like, because if that data is correct, maybe we should all be getting a Nobel Prize next year, essentially, right? We discover something with a negative thermal conductivity.
Yeah.
That is physically impossible. Okay.
Yeah.
All right. So let's look into what the problem seems to be. Can you go into full screen mode, please?
Yeah. Okay.
Cool. Another piece of advice that my old advisor gave me. When you give talks, you have to make the font comically big, because a lot of people don't see that well. So make the letters, the font, make it big.
Make it bigger.
Like, you will not be charged money if you make it bigger. Students tend to be under the impression that if they make things bigger, that's gonna come out of their pockets, which is something I don't understand. But then again, when I was a student, not so long ago, I would also do the same. So this is just a piece of advice for the papers, for the presentations, for your own work. Make the font bigger. People will appreciate it. Like, beyond me, I will be fine with whatever you guys do. Like, Kedar, your thesis committees, your people that present at conferences, they will appreciate it, okay? So please make fonts bigger and label things nicely. It will be really beneficial for you in the long run. Anyway, so total thermal conductivity. Cool. What is the total thermal conductivity of pristine germanium telluride from the papers, from the references that we have? It would be useful to overlap it here as some sort of quality control. So we know, so in my experience, like, the hardest part is always to getting the baseline correctly.
Yeah.
So since we are using a new synthesis technique, we need to make sure that our baseline is the same as in the literature, okay? So let's see the thermal conductivity. Yeah. Okay, cool. Okay, so we're getting not only the same range, but also the same shape.
Yeah.
right? Okay, that's really good.
I think
That's, yeah, I think so. I think so. I think so. Okay, let's go back to our data then. So I'm still looking at your Word document, Yutin. I don't know if this is what you intended or not. Wonderful. Okay.
Okay.
Go into full screen mode, please.
Full screen.
Okay. So, yeah, we're getting the same shape and the same range. That's really good. As we dope, our thermal conductivity lowers, obviously because of point scattering, low-lying acoustic phonons, which is what carry heat in semiconducting materials with semi-covalent bonding. So that's well known. That's fine. Our thermal conductivity decreases with temperature, as it should be, because this is a phonon-dominated system. Above the debye temperature, all the phonon modes are occupied. So it's a matter of scattering, and scattering decreases as T to the -1, which is roughly there. Obviously, the lattice thermal conductivity of SPS germanium telluride is wrong.
Yeah.
Are you sure you calculated it correctly?
I think I checked with Chen Guang, and
yeah,
he said for the 3 graph, the formula is correct, but I don't know it's data problem or something.
No, it cannot be data problem, right? Because the total thermal conductivity looks pretty much like the total thermal conductivity of the paper you just showed me.
Yeah, but maybe for CTA, for the electric transport, there is something wrong.
Maybe. So did you measure the electric transport in the sample that you used for SPS?
Yeah, but the data I showed here is the data I joule heated and then SPS, but this one is not properly joule heated, so I doubt whether it is the problem.
Then that's the problem.
Yeah.
Now you know the problem. Now you can fix it.
Yeah. So we wait for that correctly synthesized one.
So the problem is that you need to remeasure in the CTA.
Yeah.
Okay, that should be pretty fast, no? What's been measured right now in the
it's
CTA?
not the remeasure. It's because we don't have the FA data for the sample that we correctly joule heated and then SPS. Because for this thermal conductivity, is from the sample that we SPS but not joule heated. So that's the problem.
Okay, then you shouldn't be showing it to me. Because it's not.
Yeah, because we only got this one. We got
I understand. Okay. Another thing, you guys, look, the point of these meetings are not to show me how much you've worked. I already know all of you work. I gave my personal recommendation for all of you to get admitted to this PhD program. If I didn't think that you can do it, I wouldn't have recommended any of you. Okay, I already know that you guys work. The point of these meetings is to see where the project is, see how we move forward, or see if we stop. If it's data that you know cannot be trusted, don't show it to me. Just tell me, look, this happened. I'll be fine with it, okay? It's not about quantity, man. It's about quality.
Yeah.
I mean, obviously quantity too. If there is a month and you guys haven't done anything, that's a problem. But that's never gonna happen, okay? So please, make sure that you use the correct thermal conductivity and the correct electrical conductivity. Remember, we do synthesis, and because we cannot access a power source with enough current yet, we will. We are working on it, and we will install it in Create in NUS, in the new lab that we are building there. Okay. We do the synthesis with joule heating, so we don't have to use a furnace. And then we do SPS simply to consolidate, simply to densify and have a dense solid that we can cut and measure transfer properties on. Okay? So the data has to be comparable. We need CTA before SPS and after SPS, and we need thermal conductivity, obviously after SPS, and the data we'll put in the paper will be the SPS. But we need to know what happens electrically when we go from one to the other. And the data needs to be comparable.
Yeah.
If you don't have it, it's fine. Sadly for us, our thermal conductivity doesn't depend on us.
Yeah.
Right?
Because in CTA, I noticed that it's not quite similar to the trending to compare to the graph in the literature. So especially in the low temperature. So I doubt whether we should use SPS or just stick to Joule heating.
Because we have no alternative at the moment, because Joule heating alone cannot produce pellets for good thermal conductivity measurement, right?
Because I'm now working with Chengguang and Delvin, and Delvin was compiling the, I think there's a program to control the synthesis temperature, and they can control here is the video. So they can control the synthesis time and the temperature, and the rate of the temperature increasing and decreasing.
Yeah, the rate of cooling, I don't think so. The rate of ramping, the cooling rate, I already told Delvin, I don't believe it. You're gonna have to prove it to me first. I don't believe it.
Working. So
because he does not control the heat dissipation to the surroundings, and he's not really measuring it correctly.
Yeah.
So for the 100th time, I have to tell him that he does not do that. Oh my God, you kids! The day that you start listening to me, your lives are gonna improve. But anyway.
And I use it for this one, for the 5% cadmium doping, and I think the palette seems pretty good, but I don't have a photo. Chengguang says the quality of the palettes is really good for the Joule heating.
Have you cut it and seen how it looks?
Yeah, I have cut it, and
how does it look?
Yeah, I sent it for the SPS. This one is for SPS.
I mean, obviously, we want to skip the SPS because it adds more imperfections and it slows us down. Ideally, we want to do just Joule heating.
Just Joule heating.
Obviously, right?
Yeah, so next Monday, I can try to work. I have some powder for the pressing. So next Monday, I can try his program.
Yeah,
to synthesize the pressing one. And I try to cut the LFA sample without SPS.
Yes, if you can do that and you can get a sample for that LFA that looks regular, because the geometry is very important. We never got accurate data because we did not have a good geometry. If you can do that, then we forget about SPS and we focus on that because it's so much faster, right? Like, no point.
Yeah,
and the data
I can do that.
Yeah. Constant temperature. Yeah. I think it's good because if we do it at constant temperature, we can start like doing like undercooling experiments, which is a really nice way to do kinetic synthesis, right? That I believe. It would also be nice to see the effect of like the heating rate. So you do multiple synthesis using different heating rates, and then you see how the microstructure looks like. That could be quite interesting as well. But that's like further work, right? Like at the moment, let's focus on getting like the thermal conductivity. So please cut the pellet, see how it looks like. And if you can cut a regular shape with a density, measure the density, obviously. If the density looks like it's more than 95% or 95% of the theoretical density, then we can forget about SPS and focus only on the Joule heating.
Yeah, okay.
Which will be so much better for us, honestly.
Yeah.
Yeah.
Just give it SPS.
Yeah.
Okay, I can do that next week.
Okay, perfect. Please do that. Remove the thermal conductivity that is not from the same samples.
Okay.
Leave only. By the way, let's see the ZTs. I want to see how does it look like.
What
Next
data?
slide. Next slide. There.
This slide. Okay.
So, which data here do you trust?
I think because the last three, and because the selenium doping, I think the selenium has been evaporated. So there is no selenium in this
That's
sample.
fine.
So
that's fine.
I think this is a bismuth doping one, but I'm not sure. Yeah.
So
and for the bismuth doping, it's not correct.
So the bismuth doping is not correct. So
yeah, because the thermal is really red.
Yeah, it looks really odd. Why? Why does it look like that?
I don't know. Its K total is not correctly.
K total is not correct. Okay.
Yeah.
Then remove it. But how about the others? The purple and the green ones?
The purple and the green one.
Are those data that we can trust or not really?
I think it's all right. I don't know.
Were they measured? So have the electronic properties and the thermal properties been measured on the same material or not? It's a simple question.
Yeah, it's the same material. It's the previous Joule heating sample.
Okay. And the LFA was done on an SPS sample or not? Okay. So essentially, this data is just Joule heating, right?
Yeah, just Joule heating. Only the black one is SPS.
Okay, perfect. So the way I see it, the black one we cannot trust because the electronic properties are not corresponding to the thermal properties.
I can plot this one, no Joule heating and SPS sample, CTA, but eventually it's not a Joule heating one, so
then forget about it.
We don't need to plot it.
No need. Remove it, in fact.
Yeah.
Okay. And then the red one, I think the problem is that you are... What is the problem with the red one? What do you guys think is the problem? I don't see the problem.
The K total shouldn't be a straight line. It should be go downwards.
There are cases of that
this one, the first graph is okay. So after K total minus the first one, it go upwards, so it's not correct. It should go downwards.
So the electrical property was measured on what?
Yeah, it's measured.
Yeah. No, I can see that it's measured, but like measured on what? Is this an SPS sample or is it a Joule heated plus SPS sample?
No, for all these color lines, it's all the non-SPS sample.
No SPS sample.
Yeah, I just compared with the previous one. Yeah.
Yeah, I think that thermal conductivity is not correct. Probably the pellet had a weird shape and the LFA measurement is simply wrong because of the geometry of the sample. Yeah, the other three look good though. Like that's data that I think it can be correct. Decreases with doping as it should, and the limits are not so far from the literature. And the ZT is pretty good, so that's good data. Okay, good. You can add another slide at the end, please.
Another slide?
Okay, cool. So this is gonna be the to-do list, and next week when we meet again, we're gonna start with this slide. See the list, see what has been done and what's pending, and we will discuss what's been done and why what spending is pending. Okay? So what's in the to-do list for next week that we have discussed?
I think first I will do the pre-sting because I have the powder.
Write it.
Yeah, I can write it.
Go to slide number 10.
Yeah.
And write it down.
First,
trust me,
I will do pre-sting.
It will save you time.
Pre-sting, Joule heating synthesis. Synthesis. How to spell synthesis? Sorry.
Like this. Yeah.
Yeah. Okay.
What else?
Next Monday. And with this program. I think Jen, I will send all the cadmium doping one for SPS.
Write it down.
Yeah. think there is DSP file already in the folder.
Yeah.
With the previous, I think GeTe tested them previously.
The problem is that we don't know which temperature we should be using, right?
Yeah.
The reason why I like not controlling the temperature is because the melt would melt at the melting temperature and then you decrease it, right? So, and also I haven't seen any time temperature profiles here, right? That should be added as well.
Mm-hmm. Okay.
What else is missing?
And anything to... I think the folder is still a bit messy. Maybe I can do to organize it.
That's fine. No problem. Yeah. Let's. That's very useful, and I thank you for it.
Yeah, I can ask for the missing data here.
Missing data, yeah, good.
Yeah. Data. And also, I haven't do the 5% basement doping for the XRD.
Okay.
So maybe I can add the XRD for 5%. SPS. Yeah.
It would be good to have the time versus temperature profiles as a part of the data as well, by the way.
Yeah.
And I know for a fact that you measure them, right? Then we should add them. They are extremely useful.
Sorry? Yeah, I only used 45%. I just used the sample to try the program, not for all of the sample. So I can try to start from pristine because I have pristine sample.
Yeah.
Pristine powder. Separate the graph.
Okay.
For XRD and
transport.
And transport.
Cool. Okay.
Anything to add?
Thinking about it. Janata, anything else? Yeah, refinement, yes.
Refinement.
Yes.
Okay.
Okay. So I think number one is quite interesting. Because if we can make sure that we have a regular shape that we can get good LFA data on, then that will help us a lot because we don't need to SPS, we don't need to waste time doing SPS. So, I mean, the advantages are obvious, right? So please prioritize number one.
Okay.
At the bare minimum, it'd be good if you could have an XRD pattern of it. So we make sure that like our XRD still matches. I really like using XRD as a fingerprint for sample quality. So it should match. And then if you have electronic transport, that would be really good, especially because we can compare it with our previous transport and the literature to see if it's good or not. And then the density, right? Like it has to be dense. It has to be at least 95% dense.
Yeah.
And it has to be big enough so that all the LFA, all the laser spot can be on the sample and not have any beam spill, which is what I suspect happened in the thermal conductivity measurement.
Yeah. Also increase the sample thickness to 1.1 because in previously, I think because geranium material has really high thermal conductivity. So I think the sample needs to be thick.
It doesn't have to be very thick for LFA because you need a certain transmission. So it cannot be that thick. I think the thickness that works pretty well for us is like 0.7 centimeters or like something like that. I don't remember the specific value, but like you can look at our
Yeah, because I discussed with Chen Guang, and his material have much lower thermal conductivity.
Yeah.
And he used 0.7 or 0.6 or so.
Yeah.
And he said for my material, especially for this material with this high thermal conductivity, they should be higher than one
it doesn't have to be actually, but like, it doesn't hurt.
So I cut it around 1.
Okay, around 1 is good.
Yeah.
Good. Try to stick to 1 then, so that the variance between samples is minimal.
Yeah, okay.
And then, okay, good. Okay. Yeah, I think that's it. I can't think of anything else, to be honest. Can you guys think of anything else?
I think that's all.
Okay. Okay. Well, all of them, obviously. We're already doing the synthesis. What are you asking me? The SPS is a means to an end. It's a means to ensure that we have a sample that is dense and has a regular geometry to get good thermal conductivity data. If it were for me, I would never have done SPS. Why? What? It has no advantage to us. It only adds time, effort, and the data is worse. What are the advantages of doing SPS exactly? If you can give me one, we will add it to our workflow. But as it stands, I see no advantages. So you tell me, why do you want to do SPS? We do it because we have no choice. Hopefully, UTing succeeds on Monday with number 1, and we have to forget about it. And we can't forget about it, as a matter of fact. So,
okay.
What I think should be interesting, we need larger ZT, man. Like, if we could get a ZT of like 2, that would be really, really good. But for that, we will need to keep adding dopants. So I think another thing we can do is so can you go to your XRD?
XRD.
Yeah. So you see, like, I see how thank you. I see how the bismuth is saturated already, but the cadmium is not. We should continue adding. Oh, you have the 5%. Well, you're just not here.
Yeah, right? I can find the graph
no, you don't need to,
plotted.
Yeah, but you don't need to do it now. But we need to do it so that we know. Essentially, we will continue adding dopants until they saturate, until they cannot fit in the lattice anymore, and then we switch, right?
Yeah,
that is the logic here. So the antimony
here. Yeah.
Okay, cool. Let me see. See, this is a really nice graph. Thank you. Yeah. Do we have thermal conductivity for the brown and the yellow samples?
You mean on the right, this brown?
Nope, the one that you showed me.
This one, this one, the brown?
Yeah.
I think no.
No. We should get thermal conductivity for that, because I think the data is going to be really, really good.
Yeah.
So,
but we need to resynthesis.
Okay.
We don't have the alpha sample.
Okay. So, okay, perfect. So please go back to your to-do list.
To-do list.
Okay, so I'm sorry. So is this folder in our shared folder?
Yeah, it's in the share folder.
Okay. It is the, yeah, must be this one. Okay. So, okay, now it's in an order. So now it goes from 1 to 2, 1 being the thing that you should do first, and 6 be the one that you should do last. Because if you succeed at number 1, we don't need to do number 6.
Yeah.
That's evident, I feel, right? Missing data very important, refinement important, but not that much, and yeah, that's it.
Yeah. Okay.
Hopefully number 1 works. So another thing we should do for our own clarity is
yeah. Okay.
So what a workflow figure is actually I can show you in my own work. Let me find a workflow figure that I've been working for the Catalysis project, and I can show you guys, like, because that's gonna be one of the first figures in the paper anyway.
Okay. I need to stop the sharing.
I think my sharing will overrule yours, so don't worry. There we go.
Okay.
So this is a workflow figure. So it shows how it's done versus how we do it. And you have different blocks. So in my case, green blocks are synthesis. This is like testing, and blue blocks are characterization, right? So you guys can think about doing a figure like this for our own work, right?
I think I cannot see the screen.
You cannot? Janta, can you?
Sorry. Oh, yeah, I can see. I can stop sharing, and then I can see the.
Good, wonderful.
Okay,
so this is a workflow figure, right?
Yeah.
And we should do one of these for our own work. So the traditional method, I think Jayanta can do this. Jayanta can do the traditional one. You think you can do the other one.
Yeah, okay.
So you guys can split the work, so it's not a lot for like one person only, right? Point is that you show, you know, how to explain it. So the point of these figures is to show not only throughput, so gaining throughput, gaining time, right? Like, how much fast can we do things? How better can they be? And how many more of a unit can we make? Does that make sense to you guys? So you can add times and how many samples and everything. And at the end, you can calculate how much time does it take to make 1 sample or to make 10 samples, right?
Okay.
Chengguang is familiar with this because we've done it for my other paper, for my synthesis paper, right? So
Yeah. Okay.
it will help you understand what do we do, what we do, right? Like,
How many times
never forget that everything is a means to an end. Okay? We do what we need to get what we want. What do we want? We want high-performing thermoelectrics as fast as humanly possible.
Okay.
Ideally speaking, at the end of this project, we will be able to answer what is the best way to make the best thermoelectric material in the world? And how fast can we make it? The answer is very.
Yeah.
SPS is a problem. You know, if I wish we had our own LFA machine, you know, like sadly the one in NTU, it's too big. Like I don't think we can make 12 millimeter diameter discs, right? But the one in IMRI is 6. The problem is that it's operated by people in IMRI that are not in our team. So they have a different schedule, you know, like. Yeah. Yeah. Why not? Sorry? I mean, if we could measure it ourselves, it would be so much better because then like, you know, like everything is faster, depends on us, everything is in the same place. It's great. But I don't know how easy or hard is it going to be for us to be able to measure it, right? LFA is hard. LFA is really hard. Okay. So, but you know, it's like everything else. It's hard until you do it. That's what I can tell you. Okay, then. Everything clear then, right? You guys, this is very productive. Holy cow. You guys have done a phenomenal job at presenting the data and at presenting it and explaining it. This is really good. You think I'm gonna see if we have time for you to present next Tuesday?
Next Tuesday?
Because Jayanta is already presenting his other work. Please make sure that Kedars knows that copper tin telluride is not a new compound because I told him and he told me I was wrong. So okay, because he was under the impression, and I was like, I don't think so, because Jayanta told me that the magic here is that the properties have not been measured, which is really good, right? Like it's a very good, it's a clever way to do it, but just make sure that he knows so he doesn't say the wrong things to the wrong people, essentially, right? Like, yeah. Yeah, I don't think we have a single. I mean, you could always like try to make our materials and try to fish up a single crystal, but that's gonna be very hard. I tried to do single crystal AST, and I never found a large enough single crystal in our samples because they are highly polycrystalline. I don't know what type of furnace are you gonna use for the single crystal growth. Probably there are probably in NTU. I just don't know who has them. So if you need one, Kedar will get you access to it. So it's just a matter of asking. Up to you. Oh yeah, go on. Go. Yes, of course. Yeah. So yeah, but by trial and error, trial and error. We try different recipes at different ball to mass ratio. We tried different times, and then we found one that worked for us, and we stuck to it. XRD, transport, and SCMEDS. Yeah. Yeah. Well, that depends how fast you work. I mean, I don't know what to tell you. Yes, it will take time, but it's the first step that you have to try. I think the advantage is that ball milling is really not that important at the end of the day. So, for instance, this is my experience, right? Like, I'll show you since you guys are here. I'd rather show you than explain it, right? It's always nicer. Um, so for my catalysis project, right? Like we did like ball milling first, right? Turns out that like you don't even need to do ball milling, right? Hand grinding works for us. So here's an XRD pattern of my powders, like ball milled and hand grinded. The pattern is the same. So hand grinding in my case works for this particular precursor, right? Like because that's how it works, right? Like so you need to take into account precursor size, precursor hardness, and also what it is that you want from ball milling, right? Like do you want to form a phase already and you want to use it as a nucleation path? Do you want to just mix it? Depending on what do you want, then you need to pick, right? Yeah, yeah, yeah. Okay. If it works, it works, right? Like chemical similarity is always your friend. Like if you're trying to make, what compound are you trying to make? Let me see if I can think of something. The copper what and what and what? Okay. But you've already done it, right? You already made it. Doesn't matter. It's already made. But if you want to do it, mhm, yeah. I remember, yeah. I remember. No, they are not gone. Probably they redissolved. Yeah, you will never get rid of it. It's very stable. But I remember in my last group meeting, I remember that like you show your data and you had a less than 10% of copper telluride impurity, right? Yeah, so that's pretty good already. Okay. And what okay. Hmm. Right. Okay, I see. Um yeah, that sounds good. But I don't think the ball milling is that important to be honest. Like in my experience. Yeah, it's fine. You've already made a face. You already got the face. Clearly what you did worked out. Right. So I don't see why you would go back and like work on the ball milling again. I mean, if you want to do it, do it. Like you're the owner of your own time. But I don't see I don't see why would you do it, you know? Huh? Yeah, heat capacity, but I think at low temperature. You can only measure from low temperature up to room temperature, I think. I think so. Oh, you can't? Ah, okay. Then you can't. You could measure, you can do DSC in NTU, right? Why do you want to measure at low temperature exactly? Sorry. Wow. And at what temperature are you measuring your transport? And how is the low temperature data going to tell you anything about the high temperature data? I fail to see what interpretation would you do there. Mhm. No, not at all. How is an optical mode cannot scatter an acoustic mode? They can mix, but they don't scatter each other. They can for sure mix. That's when you have a band crossing, right? You have mixed scattering, but they don't scatter each other. Okay, if that's what you mean, yes. But you can see that from the thermal conductivity itself, right? Okay. Yeah, you're thinking about this the wrong way. You have a problem and then you use tools to solve the problem. No, you don't just do everything and then see what happens. That is just bad science and you should stop right now. Because your committee is going to cook you if you do that. If you are just doing things and do not understand why you're doing them, you should stop and not do anything at all. I have seen people fail because of this. They just do everything and then they have no idea what to do with it. This is what you were doing. And I don't know how Kedar has allowed you to do this for this long. But please don't tell him, just don't tell him anything you said that to me in the last 2 minutes. Because he will cook you immediately, okay? If you need to do in situ XRD because you need the data, then you do it, okay? Okay, okay, okay. To what? If you already know it decomposes, why do you need the data? Can you not check a phase diagram for that? No, but you have a pseudo phase diagram, right? You probably have copper telluride and tin telluride, and then you can see that, right? You need to stop doing things because you want to do them. That's just bad science. You're not going to get anywhere like this. Please believe me. It's not about what you can do, it's whether you need to do it. Also, all these things cost money, by the way. So if you just do things because you want to do them, that's fine by me, but don't tell Kedar. Because he will start asking you why you're doing them, and you clearly don't have an answer for it. So what's the point of all of this, right? Start thinking about why you do things before doing them. So it's a good advice I'll give you. Your thesis committee will tell you the same. I saw them telling it to Chen Guang during his thesis committee. They asked him, why have you done this? He had no answer. And they basically said, like, you'll never graduate if you don't know why you're doing things. You know, there's a difference between being an intern and being a PhD student. When you're a PhD student, you need to know what you do and why you do it. So the earlier you get that mentality in, the more you start succeeding, to be honest. And the faster as well, really, like, you know, for sure. So if you need in situ XRD, you can do it. You will not do it in Singapore, but if you convince me, I will do it for you here in Berkeley, where I can have access to one. In fact, I'm going to measure my own samples in an hour. So if you need the data, I'll get it for you without question, immediately. But if you just want to see phase separation, you just take the sample after you measure CTA, and then you put it in the XRD, and then you will see the phase segregated. You don't need to do in situ XRD. If you need heat capacity at low temperature because you're doing low temperature thermoelectrics, then measure it. Or hell, I'll measure it for you if you want. But if you just want to do it just to see it, I mean, do it if you want, but like, don't waste my time with it. That's all I'm going to tell you. All right. Anything else? No? Wonderful.
Yes, for next week's presentation, yes, I need to present it next month, Tuesday, right?
Let me ask if we have time for you, because we are a lot of people. Everybody's gonna present, and these are like short presentations.
Yeah.
So
how much time?
I don't know, 5 minutes.
5 minutes.
5 to 10 minutes, yeah. So
Okay.
I know for a fact that I can do it. I know Jayanta can do it too, but can you present all of these in 5 minutes? Can you basically tell me the whole project in 4 sentences? That's how it boils to it. Like, this is a good preparation, and you know, like you're starting your journey, so we don't expect you to be able to do it. Me, I must be able to do it. Jayanta knows how to do it, and he will be better as time goes on. You will get better in like a year or so. We don't expect you to be able to do it now, but if you can, it's good practice for you.
Yeah, I think I can. Is it online?
It is
presentation online.
Well, you think I'm in Berkeley? Do you think I'm gonna take a flight to be there on Tuesday?
Yeah. Okay. Okay.
I mean, don't get me wrong. I would love to be able to be there in person. I would love it, but you know, I don't think I will be happy if I charge him $4,000 just to be there for an hour.
Just
right?
for a meeting.
I think he will not be very happy with me, and I'd rather not him get angry with me.
Okay.
Right? So
yeah,
because of me, sadly, it's gonna be an online meeting. Sorry.
Okay.
But
and and I think what data to add for the presentation, especially if we need to talk about the SPS or all the joule heating sample.
I think Jayanta can help you with that. He has much more experience presenting and arranging data, so he's much more qualified at this point to do it than me, because he's been doing the project for longer than I have at this point. So I'll leave it to Jayanta. He knows what to do, so work with him. Jayanta, please help her figure this thing out. Thank you so much. I think between the two of you have done a great job at presenting the data today to me. Kedar will not have as much time as I have. So we need to get the message through, right? Which is that what we've been doing, again, you guys, it's obvious that you work a lot. Like it's self-evident, okay? Nobody questions that. The point of these meetings is to learn something new and to know how do we move forward. We don't need to go through every single piece of data that you've ever collected. And to Jayanta's point, you don't need to collect every single piece of data that you can. You need to collect what's needed, okay? And present what's needed. So you've done a good job at this today. I feel like you'll do a very good job on Tuesday as well. So let me see if we can have you present this, you think, and if not, I will present on your behalf. Okay?
Okay.
Wonderful. This is really good, you guys. I'm very happy with the progress of this project. We're getting really good values of ZT. And if only we can, you know, skip the SPS and just do the joule heating, that would be so good, you know, like that'd be super, super good. So we'll try to do that, okay?
Okay.
All right, then. I'll see you guys next week around the same time then, okay?
Okay.
I think we should try to do this weekly because it helps me follow the project. And I think it's good for everybody to get feedback regularly so we can like, you know, and then if there are questions, you can ask me directly. I can dedicate an hour of my time to do this. I want to dedicate an hour of my time to do this rather, okay?
Okay.
So if that's okay, I will send you a calendar invite again, like in 20 minutes, okay?
Yeah, okay.
Perfect. If there are more questions, text me. I will be available, so text me. If not, I'll see you next. Jant, I'll see you next Tuesday for sure. You think if I don't see you next Tuesday, I'll see you next Friday, okay?
Okay.
All right. Cool, guys. Have a good weekend. Thank you so much.
Okay,
great work. I'm very happy about this. Congratulations. You've done an amazing job, both of you. Bye-bye.
Bye-bye.